Art gallery problem. First, let's take a look at the problem statement. Actually, the problem statement is much easier to understand than the actual solution itself, which we'll see through the course of this video. Okay, here's the problem statement from brilliant.org. Given a layout of a museum or an art exhibition, whatever you want to call an polygon, an enclosed polygon, which is more important than the actual idea of what is that, a museum or art exhibition. What's the minimum number of guards needed to guard every point in the museum such that it's safe? This problem is often called as the art gallery problem. It's an example of problem that includes many fields of areas such as geometry, discrete math, and optimization. And optimization is a big, interesting term to describe this problem actually, because as you can see in the next statement, it's an NP hard problem. NP is the abbreviation for non-deterministic polynomial, which is a fancier term for a problem which doesn't have an efficient solution till this date. Other NP problems which you might have heard or come across are the traveling salesman problem or the Hamiltonian chore in a graph. Those two are the one which strike my mind when we say NP problem, and those are comes under graph. Okay, to get an intuition of our problem, first let's um, get a visualization of this right now. Let's say this is the art gallery which you want to protect. For polygon of this, a single guard will be sufficient. And I forgot to mention it. The guard has a 360-degree vision. To say that, you can think of a 360-degree camera which has a whole side of coverage wherever it's placed at the center of location. As you can see in this includes polygon, which is a triangle, a single guard will do the job just fine. And same goes for this rectangle also. A single guard placed over here will just do the job fine. But you won't be getting the simple polygons such as these for this kind of problem. Let me show an example of what it actually looks like. Say you're given a polygon such as this one. As you can see, a single dot over here or camera over here or guard, whatever you want to call it, wouldn't do the job. As you can see, the line of sight of vision for guard or the camera won't be sufficient enough to cover this area. Or if you place the guard over here, that won't do the job either. So the only possible solution you can think of as for this problem is that placing guard in every vertex of this polygon. As you can see, the blue dots represent the vertices of this polygon, and if you place the camera or guards in at every vertex, the place will be secure. But that wouldn't be an optimal solution. That's where the solution of the problem comes to us. We are trying to prove in this solution that for n vertex polygon, such as this one, n by 3 number of guards or camera would be sufficient enough to cover the whole polygon. For example, this has how many vertices? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 vertices are there. This is a 9 vertex polygon. So according to our proof, we need only 3 cameras for this one in the worst case scenario. And that is, so by placing a camera over here, and over here, the job would be done. And for the sake of this problem, we are going to assume that the guards are placed only at the vertices for proof. So we cannot place the guard over here where I placed the second one. You must be placing over here, over, let's say over here, or here, which will get the job done for this problem. But how would it be so sure of that n by 3 guards are be suffice? That's where our solution approach to our problem comes to our mind. Okay, let's see the approach to our problem. First one is which we're going to try to prove is that for any convex polygon is that every internal angle of the polygon must be less than 180 degree. One guard is sufficient. As you could have noticed, the first example which I showed you over here was two polygons which has internal angles less than 180 degree. As you can see, the internal angles of a rectangle and a triangle are less than 180 degree. If you want another example, even for a pentagon, a single camera would be suffice, as it's a 360-degree view. It will suffice the solution. But for the approach of this problem, we are going to place the camera at vertices, and even if we place the camera at the vertex, such as this one, you will get the whole side of the polygon. So same goes for the rectangle and the triangle also. So as you can see over here, by placing a single guard over here, the whole polygon gets the side of coverage of the camera. So the first approach to our solution is that a simple idea is that for any convex polygon, a single camera would suffice. Okay, this is where the problem gets interesting. As for the next one, we're going to be needing for the next approach, which is called triangulation. It's a simple concept in itself, that the concept is such that any polygon, any arbitrary polygon can be triangulated. I'll better show you, which will be more easy to understand. So you can see over here, in a triangle in itself a triangle. So it's triangulated. It satisfies the definition. And for four-sided polygon, which is a rectangle over here, if you connect the opposite vertices of this rectangle, as you can see, is triangulated now. And this goes for the same for the pentagon also. As you can see over here, if we connect this vertex to this one, and now we will be getting a triangle and a parallelogram, or whatever the polygon you want. I think this parallelogram. And as you can see over here, now we'll be getting a two polygon. Just think of slicing this pentagon into two polygons as after connecting these edges. One is a triangle, which is n equal to 3. As we have proved earlier, n equal to 3 is a triangulation. This is possible. And for n equal to 4, now this parallelogram has 4 sides. So for n equal to 4, we also proved that triangulation is possible. So for n equal to 5, the same applies. So I am trying to say is that by induction, by mathematical induction, you can say that for any arbitrary polygon of n vertices can be triangulated. So let me show an any a complex polygon which can be triangulated. Let's take this image. My bad. Copy image. Paste voice here. Come. You can see over here, this polygon over here can be also triangle, which we earlier saw for the getting an indication of this problem. So you can see by connecting these two vertices and these two vertices and the vertices together, we'll be getting a triangulated polygon. So by induction, we can say that for any n-sided n-vertex polygon, it can be triangulated. So they're clear in the second step. Now comes the part of the solution where we will be proving that n by 3 cards will be sufficient enough to get the job done. It is called tricoloring, or whatever you want to call it. It's a similar concept of bipartite of a graph. I don't know whether I should explain over here, but if you know bipartite of a graph, you might think it of that in the same way. A similar way of bipolar graph, but here we will be using three colors instead. As I said earlier, replacing cameras at each of these vertices will be the job done. But we cannot afford n cameras for n vertex polygon, which will be uh, not an efficient solution for this problem. So what I'm trying to say is that, let's take an example. As you can see over here, this is a polygon. First, we are going to triangulate it. I didn't show the triangulation steps of this polygon, but let's assume. But as we proved in second step, any arbitrary polygon can be triangulated, which we proved by induction. So this polygon can be triangulated, and the concept is that tricoloring is that any two adjacent vertices wouldn't share the same color. As you can see over here, red, blue, green. You cannot have a, say, a red vertex over here, which will violate the concept of triangulation. So as you can see over here, there are no two connected vertices which share the same colors as the tricoloring is just up to you, but the concept is such that you can see for a triangle there will be, let's put the image over here. Let's say this has a red color one, this has a blue color, green color, sorry, and a blue color. So the concept of tricoloring is that there are two no connected vertices which have the same color, and the proof is that by placing the camera at one of these vertices, you'll be able to get the coverage of you'll be getting the solution of n by 3 this problem. Let's see it over here. So you can see the number of vertices of red are equal to how many red vertices are there, cameras are there, 1, 3, 4, 4 green comes on 3, 4 same, and blue will be 3. So the total number of vertices are actually blue is 3. I'm bad. It will be around, it's a 11 vertex polygon. So by the proof we can say that by placing the concept such that after tricoloring we can place any guard at one of these corners. Let's say a blue corner. Let's say a camera placed over here, this blue vertex and this blue vertex, and that one too. The camera is placed in this blue vertices. By placing any guard at one of these corners, we can get the complete areas covered by the triangle sharing that vertex. For example, this camera see the can get the coverage of the triangles of this one, and this triangle, and this triangle. Same goes to this. This triangle doesn't share any other triangles. This word isn't shared by any other triangle, so this will be getting the coverage of this one. But again, if we take this vertex, the triangle shared by this vertex are this one, and this one, and this one. So a single camera will be enough to get the coverage of these 4 triangles, and this blue will be taking care of this one and these 4 triangles. So what I'm trying to say is that any guard at one of these corners can see the areas covered by triangles sharing that vertex. As we have taken we chose to place the cameras at blue vertex such that blue vertex are the lowest in number in this polygon. So by the proof which we came to prove is that for n-sided polygon, n by 3 cameras would suffice. As you could see over here, 11 by 3 comes around less than 4, which is the number of cameras, which is the number of vertices of blue vertices over this polygon, which is 3, which is less than 4. So this is the proof of the algebraic problem with this approach one, which as you can see, remember the steps. For any convex polygon, which is a triangle, a single camera would be sufficient enough to cover the whole coverage. So as you can see, this is a triangle, this is a triangle, this is a triangle, this is a triangle. All these are convex polygons. So a single camera will do the job just fine. And the next one is the triangulation. For any arbitrary polygon, it can be triangulated. As you can see, this is a complex polygon and it's been triangulated by connecting the vertices. This one. The triangulation concept comes to aid the first one, which we first step in the approach, which is any convex polygon has less than 180 degree, has one set camera sufficient. The third step, which is tricoloration, is the actual aid to pick up the vertex which is less than numbers, so that we can place the camera in the colored vertex which is less than number. In this case, it's blue. Now you can ask me doubts as a question which for this polygon it's true, and for any other polygon it will be true. I'll even show you an image. As you can see, this proof is going to be true for any arbitrary polygon. As you can see over this in image, it's again be tricolored, and the vertex to place camera has been chosen by the number of letters colored vertex which is in lower number. In this case, it's going to be blue again. As you can see, green has 5 vertices, red is in 4, but blue is in only 3 vertices. So placing the camera at blue vertices, the whole coverage will be got. But the actual question is, how do we know that the minimum number of cameras would, what is the minimum number of cameras which is required to cover the actual polygon? And as I said at the starting of this problem, this is an NP hard problem. There's no efficient way of telling it that this is the minimum number of cameras to be placed for the safeguard of this place, as it's a non-deterministic polynomial, as there's no way to get an efficient solution for a polygon at this stage of computational geometry. But in the future, maybe we may get a straightforward solution for this one. But as far as this theory stands now, this is a useful approach for solving this problem. And thank you for listening.